Michio, extra dimensions is front and center in the scientific world. No longer just science fiction. I want to understand how it works in string theory, in fundamental physics, and then potentially in cosmology in large extra dimensions. How significant is this in our understanding?
Let me tell you a story. When I was a child growing up in San Francisco area, I used to visit the Japanese tea garden and to visit the carp swimming just beneath the lily pads in a two-dimensional pond. I used to spend hours looking at them. They would swim forward, backward, left and right. Their eyes were to the side, and they couldn't see me. I was in the third dimension. I was in hyperspace. They were totally unaware that there was a universe beyond their pond. And then I thought, well, what happens if I reach down and grab one of the fish, lift the fish up? Maybe that fish was a scientist, and the scientist would say, bah, humbug, science fiction, there's no world of up. Up does not exist. Well, I would grab this scientist, lift them up in the world of up, hyperspace, the third dimension. What would he see? He would see beings breathing without water, a new law of biology. Beings moving without fins, a new law of physics. And then I would put the fish back into the pond. What kind of stories would he tell? Well, today, we physicists believe, we cannot prove it yet, but we are the fish. We spend all our life in three dimensions. We go forward, backward, left, right, up, down, thinking that anything beyond our pond, anything beyond our little puny universe is science fiction. We say, bah, humbug. We can't say that anymore because the concept of higher dimensions now is the biggest game in town. You see, in three dimensions, there's not enough room to put all the laws of physics. But when you go to this larger pond, this pond of hyperspace, then all the laws of physics just fit together like a jigsaw puzzle.
In our three dimension, the laws of physics are there, we can explain things, but there are lots of pieces that seem to be random, that you have to enter constants by hand, and so you might have 30 or so constants of physics and more in cosmology, and they look like they all have nothing to do with one another.
That's right. I like to think of a crystal. Let's say a crystal, a beautiful crystal, shatters and lands on a tabletop. And they're little insect-like flatlanders living on this tabletop. And they say, let us reassemble the crystal. Well, they bring it together, and then they have one crystal. It's called the quantum theory. They assemble other pieces of the crystal. It's called relativity, theory of space-time. But then they try to bring these two chunks together, and they cannot. No matter how they bring these chunks together, they cannot. And then one day, someone says, let us go to the world of up. Let us move one crystal up and then fit it into the third dimension, and it will create a beautiful unified crystal. That's where we are today, we think. We live in a three-dimensional world. We see pieces. We see the electromagnetic force. We see gravity. We see nuclear force. Little pieces of this unified field theory. We bring them together. Now we have the theory of the quantum theory, the theory of the small, the theory of atoms. We have the theory of Einstein, the theory of space, time, relativity, but they don't fit together until you go into hyperspace, and then they fit together beautifully.
So when they fit together, what does that mean? We now learn that we need 10 or 11 dimensions, only 3 of which, or 4 if you include time, that we have, and so there are as many as 6 smaller dimensions, and what's happening in those dimensions? Why do you need 6 in string theory?
Well, today we see the world as is very broken. We see pieces of it. But at the beginning of time, when the universe was first created, that's when the crystal existed in its perfect form. We call it the superforce. A single superforce held this crystal together, but then we had the Big Bang, which shattered this crystal, giving us the shattered universe of today. When you look around you and you see the different forces, mountains, clouds, planets, it's broken. We live in a horribly broken world. But at the instant of creation, there was perfection. There was perfection in a higher dimension. This perfection cannot exist in 3 dimensions. Now, some people say, well, why 10? Why 11? Well, it turns out that there are certain magic numbers in mathematics, and numbers which have spectacular properties. It turns out that if you go to a 13-dimensional universe, a 15-dimensional universe, it's unstable. Particles would prefer to collapse down to 10 or 11 dimensions. because the mathematics shows that self-consistency is important. They're unstable. Universes in 29 dimensions are simply unstable.
And so the mathematics has shown that we need 10 or 11 dimensions, including the three we see, to make stability. And so the simplest forces or strings can then emerge in our three-dimensional world in the particles and forces that we normally see.
That's right. So in this crystal, the crystal exists in a higher dimension, but it eventually cracked apart for reasons that we are still trying to understand. And the three-dimensional world we see today is quite broken. Now, where are these higher dimensions? Look at smoke. Smoke permeates throughout a room. Smoke permeates in all three dimensions, but smoke never disappears. Smoke never floats into the fourth dimension. Therefore, a fourth, fifth, sixth dimension has to be smaller than smoke. But atoms also don't suddenly drift away into hyperspace. Therefore, these higher dimensions have to be smaller than an atom, or else our universe would float away, okay? So we think that at the beginning of time, there was this perfection of 10 or 11 dimensional hyperspace, but these other dimensions curled up, so small that atoms cannot leak into these higher dimensions.
So these are the kinds of that look from a distance as if they're one-dimensional, but when you get very, very, very small on scales that are much, much smaller than an atom, they actually would curl around each other and be like a straw.
That's right. So that the universe we see around us really is hyperdimensional, but we can't see it because these other dimensions have curled up. They're too small to be observed.
Compactification is the word that I think string theorists use.
That's right. If I have a tabletop exists in two dimensions, but I can roll it up like in a cigarette, roll it up, and then I see this one-dimensional thing, which is actually two-dimensional if I get very close with a microscope. So we think that these higher dimensions are all around you, in your body, in your living room. The pond touches the third dimension at every point. So if I have a pond and we are the fish swimming in the pond, and you ask the fish, where is the third dimension? The answer is everywhere.
All right, now we have, that's on the microscopic scale. What about large extra dimensions that seem to be talked about now in some theories of cosmology?
Well, strings can only vibrate in 10 dimensions, but in the 90s, there was a revolution that it turns out that if you add an 11th dimension, one more dimension, then membranes can exist. Not just little strings, but beach balls and golf balls can vibrate. And perhaps our universe is a membrane, in which case perhaps some of these dimensions could be large, perhaps even infinite. So once you go from the 10-dimensional world of strings, where these dimensions are very tiny, and go to an 11 dimensions, then you're talking about a whole new picture, a picture whereby some of these dimensions could be huge. And that may even explain why gravity is so weak. Gravity is a very weak force. Perhaps gravity oozes, escapes into these higher dimensions, and that's why gravity is so weak.
This so-called hierarchy problem, which gravity may be 10 to the 39th or 10 to the 40th times smaller than the electromagnetic force. It seems that these two are fundamental forces. To have such a vast difference in scale doesn't seem to make sense.
That's right. I could put sheets of paper on the table, comb my hair, and you do this in elementary school, pick up the sheets of paper. Well, I just defied gravity. The Earth weighs 6 trillion kilograms. I defied 6 trillion kilograms with a comb by picking up pieces of paper with the electric force.
Right.
That's how weak gravity is. And perhaps these higher dimensions is due to the fact that space oozes, gravity oozes into these higher dimensions.
Now if we look at the possibility of these large extra dimensions, which you said might be infinite in size, are we limited to these extra 6 or 7 dimensions other than the 3 we see, or might there be a vast number of infinite number of dimensions, as well as each one being infinite in size? How many infinities are we dealing with here?
Well, we think that 11 is the upper limit. Some people actually have looked at 12 dimensions. In 12 dimensions, you have 2 times. But in 13 dimensions, the universe becomes really unstable. I've looked at 13. It's a horrible dimension to work with mathematically. 12 seems to be the limit. And even in 12 dimensions, you have double times.
Yeah, I don't know what to make of that.
Right. But one thing is maybe we can experimentally see some of these objects, because if a universe is hovering just above you, It is invisible to you, light goes underneath, and that may explain dark matter. Dark matter is invisible, it has gravity. The Hubble Space Telescope has given us maps of this invisible matter. Maybe it's nothing but an ordinary galaxy hovering just above us in another dimension. If you read H.G. Wells' famous novel, The Invisible Man, he becomes invisible because he's blown into the fourth dimension. He's hovering just above us. Light goes underneath the invisible man, but he can look down on us. So perhaps dark matter, which makes up most of the matter of the universe, is nothing but ordinary matter of a galaxy hovering in a parallel universe just above us.
Under the thinking, gravity then being the only kind of force that can transmit in some way between different dimensions. It's the one thing that different dimensions are permeable to would be gravity. Everything else can't penetrate it, but gravity can.
That's right. We are like flies on flypaper. The flypaper represents our universe. We're stuck. We can't get off. But gravity oozes between flypapers, and therefore we can actually perhaps detect experimentally the presence of alternate universes. This is not just science fiction. Perhaps with our instruments, we can detect dark matter-like objects from other universes hovering just above our universe, because gravity oozes between dimensions.